All right, thanks everyone for coming back to, we've now got the last session of the day. We've got Rex, VK7MO. He has been doing a whole bunch of really cool things, bouncing signals off the moon, and he's here to tell you about it, basically at 10 gigahertz, and what you need to do and what can go wrong. And what can go very right as well. So, yeah, thanks.
Okay, thanks, Scott. Thanks for everyone for coming along. I wasn't quite sure about the audience, so please ask questions if I'm on a different wavelength to you guys. I guess for the hams in the audience, terms like QRP and EME don't normally go together. But it is possible, and with an open source program which is being written and continuously revised. I mean, this morning it might have been up to revision 747, and this afternoon you can add at least 10 revisions to that. So open source in this world is happening as we speak. Now, for the non-hams, just a little bit of terminology. EME stands for Earth-Moon Earth Propagation. And that means we're on the Earth, we're reflecting a signal off the moon and back to anywhere else on the Earth who can see the moon at the same time. It's 800,000 kilometres roughly there and back, and takes about 2.5 seconds to get there and back. And you've got inverse square all the way up there and inverse square all the way back, so your power is diminishing to the fourth power. And QRP is amateur terminology, in amateur terminology means using 5 watts or less. So if you think about 5 watts like a torch, pointed at the moon, reflected all the way back to the other side of the Earth, and you can communicate. Now, I should say the data rates are not great. We're talking about 72 bits per minute. But fortunately, the rules for ham radio don't require a lot of information to be exchanged to have a minimal QSO. Now, QSO is probably another term that you haven't come across if you're not a ham. It essentially just means a contact between 2 ham stations. And there are rules which say a minimum contact, the absolute minimum, you must exchange both call signs, a signal report or some other unknown information both ways, and confirmation that the above has been completed. And one form of that is as I've listed there. I call CQ, a station in England sees my CQ, calls me and sends me a report, in this case minus 25 dB. I respond saying, with his call sign, I say, R for Roger, yes, I've got your report and both call signs, and my report to you is minus 26 dB. And he comes back with Roger, Roger, Roger. Now, that completes an absolute minimal QSO. It's not the sort of thing that's going to change the world in terms of a news item, but it produces enormous joy if you do that on 5 watts around the world. So, let us move on. Now, the first EME, first echoes from the moon, were actually found by accident. And this is World War II. The Germans are developing high-power radar systems for the purposes of I guess, detecting the British bombers. And they were working on 564 megahertz, and they're running 120 kilowatts, and they're testing out their radar, and they see an echo coming back about 2.5 seconds later. And they think, something's wrong with our gear here, something's funny going on. Anyway, they didn't worry too much, and after some time, it sort of faded away. Okay, oh well, let's not worry about that. Next day, it's there again. And someone looks out and found that the moon was falling just about the time they were doing these tests. And so, for the first time, echoes, no information, but echoes were received from the moon. I guess information was received, 2.5 seconds takes to get to the moon and back. Now, the first amateur EME was done back in the 1960s. By this time I had my own call sign, and so I was very interested as a teenager in what was being achieved. These guys were using a 3 and an 8 metre dish and 1 kilowatt. Generating that sort of power at 1296 in those days would have been an enormous achievement. And they were using the old-fashioned Morse code. The reason for using Morse code is it uses much less bandwidth than, say, voice, and you can you've got a chance of getting a signal through, and that was achieved back in 1960 with Morse code. Now, going forward, this is where the open source programming becomes involved. By 2006, a guy named Joe Taylor, now Joe Taylor got his Nobel Prize for working out or proving relativity and using the Arecibo radio telescope with 300 feet in diameter or metres. And at one stage, he decided to put, he's really a mathematician, but he decided to apply his mathematical skills to amateur radio. Little story, as I was at this stage doing some work on meteor scatter and using a program that had been written by a Romanian, and we were getting reasonable results. And another American who I was working with said, oh look, we've got this, there's a guy over here, he reckons he can write a much better program. And apologies to the Americans in the audience, but I thought, oh yeah. Anyway, it turned out that this was Joe Taylor, and he had the ability to write a much better program. Initially for meteor scatter, but ultimately for very weak signal stuff that's really good for EME. And I started testing his stuff right from day one, and I've developed a very close relationship with him, and I've been able to do lots of experimental work. I'm prepared to waste time just repeating experiments over and over and over, and feeding him back the data, which has, I believe, helped a lot, and certainly I've enjoyed doing it. Now, at this stage, his program was fairly well developed by 2006, and I was running a fairly small dish, 2.4 metres, on my balcony, and working 10 watts via the moon. And that was to a station who was just up in Queensland. You can see the whole thing sort of wheels in and out, and it's all typical ham sort of operation. But we're getting close to QRP, and even getting that far was a lot of joy. Now, about this time, there was I think it was the 40th anniversary of the moon landing, and there were some guys in America wanted to actually organise EME contacts to celebrate the 40th anniversary of the moon landing. And I was fortunate enough to be able to borrow the University of Tasmania's 26-metre dish, which is on one side. And there were some guys in Holland who have got a 25-metre dish that's an ex-radio astronomy dish which has been taken over by a ham radio group. A fairly serious ham radio group, because when you read some of the literature, that they've all got PhDs in astronomy and stuff. And I said I'd take part in this test. When I got out to the university site out there, I realised that their preamps were all liquid helium cooled, and me running any sort of power next to these preamps was not going to be on. But I sort of worked out what power I could afford to run, and essentially this became a challenge in running right down. I worked out we could do it on 10 milliwatts, 10 milliwatts to the moon and 10 milliwatts back. And in fact, we completed only one way, because they were still running full power at the other end, but with 3 milliwatts. Now, probably hams wouldn't count QRP when you're using a 26-minute dish. So I don't think we can count that as a QRP contact, but it just shows you what you can do with decent dishes.
How much gain does a dish like that have?
Oh, gee, I've forgotten now. Let's try and do some sums. Oh, no, it'll take me too long. But I think you'd be up around 40 dBi, even at 24 gigs, at 10 gig, at 1296, 23 centimetres, yeah. Okay, now, first time I went up to 10 gigs, and I was just using a little offset dish and doing some tests to see whether it would be possible with a guy named Alan, VK3XPD, who's in Victoria, and his dish is actually a 3-metre dish on the left-hand side, but Alan makes things in the real ham fashion, and if you can see there's a load of bricks on a lever that's trying to balance the weight of the dish. And with that, we got down to 10 watts. Now, not quite QRP, but at that stage, that was a lot of fun. You can see my system on the right-hand side. It's only a 64 centimetre dish. You see a rifle scope on the top, which I used to track the moon manually. So getting close. Now, I was going to say this year, but we're already into next year, aren't we? This year, I got a system working with G3 Whiskey Delta Golf in the UK. He's got a 3-metre dish, and I'm only using a 77 centimetre dish, quite small, and we got down to 5 watts. Since that time, I have completed 5-watt QSOs with 2 other stations, 3 altogether. And in fact, we're getting even a bit lower than that, just with a 77 centimetre dish. Now, we'll go into some of the technical issues now, but one of the things you can do with the WSJT program, which was written by our Nobel Prize winner Joe Taylor, is you can just add noise to wave files to degrade the signal and see how much noise you can add while you can still decode it. And so if you're running, say, 10 watts and then, well, in this case, I'm just reducing power from 10 watts to 7 watts to 5 watts. And I'll explain the noise reduction on the next slide. And you can see the decoding is changing. Up here, you can see F decodes. What F means is, it actually stands for a Frankie Taylor decoder, who are two people in the States. But I interpret F means it's fully decoded all the information over the air. It hasn't needed any hints about what call signs are involved. D means a deep search, which is a correlation decoder, where if you can help it by knowing your own call sign, which you generally do, and if you can help it further by knowing the other guy's call sign, which if you're running SCEDs, you always do. So it's no different to normal ham operation. The only thing that becomes unknown is the signal report. So the D decodes are really only gaining extra information from the signal report, although they are establishing that the particular call signs were sent. If they were not sent, it wouldn't decode them. It's the difference between identifying something you know or finding a needle in a haystack where you don't know where to look. Now, you can use this added noise technique to see what would happen with this 5-watt signal if you add 3 dB of added noise. Now, what I do here is I use the same file, I just put a different time number on it, and add the noise to it. The noise is random, so you don't always get exactly the same result every time you do it, but if you do it over 10 tests, the average result's always pretty close. With 3 dB, you can see I've only missed 1 decode out of 10, so from 5 watts I can certainly get a pretty good amount of decoding at 2.5 watts. 4 dB, 50% of the time it's still decoding, and hams don't mind waiting until the next time. You know, ham communication is, when it works, you're happy, and if it doesn't work, you don't worry. Professionals don't really like this sort of communication. And if you had enough time, of course, you can wait and you'll get a decode even at 5 dB. So something like 2 watts is possible with this setup. Now we'll go into some of the technical things. A signal going to the moon and back has a propagation loss of these sort of large numbers. Now, this is in decibels, a log scale, so you can imagine this is a loss of 253 dB up to 290 dB by the time you send a signal to the moon and back. Now, the first thing you notice is 144 megs, which is a ham band where a lot of EME is done, has 253 dB of propagation loss. You go to 10 gigs, and it's up to 290 dB. It's 37 dB worse. Now you scratch your head and you say, why the hell is people going up to 10 gigs? And the answer is the antenna gain goes up the propagation loss goes up by 20 dB each time you go up by 10 times in frequency. It's a square law. And so your antenna gain for the same physical size antenna also goes up by 20 dB, and you're no worse off. But where the plus arises, you've got an antenna at both ends. So you're immediately 20 dB better off by going up to 10 gigs. Well, no, going up 10 times in frequency. In fact, if you're going up to 10 gigs, you're 37 dB better off. So that's the reason for going up in frequency. Now, system noise is generally much lower at 10 gigs. If you work EME in a city area like Hobart, I can't work when my antenna elevation is below about 20 degrees because I just pick up all this city noise. 10 gigs, I can work right down to 3 degrees, right on the horizon, and I never noticed the city noise. So the noise is much lower in the city area, at least. There is moon noise, and as you have a very high gain antenna, your antenna focuses all of its beam width on the moon. And the moon has a temperature, and that produces noise. It's about 218 degrees Kelvin. And so a person with a large dish, sort of 3 metres plus, their beam width's the same size as the moon, and they're seeing about 2 dB of moon noise. And so the hardest thing is for them to receive me, because they've got extra moon noise. With my small dish, I'm mostly seeing cold sky around the moon, and so I don't lose that 2 dB. But seeing on the QRP station, the hard job is for the big home station, because they've got that extra moon noise. Now, programs and modes. The program that we use is called WSJT, which I think by now we could call a suite of programs. It was developed by Joe Taylor, and it allows signals to be decoded up to 30 dB below the noise in an SSB passband. Now that seems a bit of a trick, and normal amateurs use single sideband and use a passband of about 2.5 kilohertz, but with Fourier transforms, you can break that passband up into little segments that are only a few hertz wide, and so instead of looking at 2.5 kilohertz wide, you're looking at 2.5 hertz wide, and you've reduced the noise by 30 dB. That's the prime reason why this sort of mode works so well, but it also works because it's got a lot of error correction and other techniques built in. It's an open source system. It's available on Windows or Linux for this conference. And just consumer grade PCs, we're starting to get to the point where you need a reasonably fast computer with a decent amount of memory to take advantage of some of the current modes, particularly QRA, which is a recent one that's only picked up, to my experiments show QRA's picked up only about 1 to 2 dB, but when you're down at this level, 1 to 2 dB is worth having. JT65 was the first mode that was developed for EME. A bit later on, Joe Taylor developed the JT4 mode specifically to cope with the signal being spread, and we'll go on to that in a minute. Just recently, this QRA mode, QRA stands for Query Repeat Accumulate Code, and it's a modern communication technique which gets you closer and closer to the Shannon limit. Shannon's got a lot owing to us because he's put a cap on what we can do, and we're within a couple of dB of that at the moment. Right. Now, lunar degradation, the moon doesn't go round the Earth in a circle. It goes round in an ellipse. And from the maximum distance to the minimum distance, there's about 2.3 dB variation in the signal you get back from the moon. And obviously, if you're going for QRP, you've got to choose a time when that's as low as you can get. Doppler shift. Remember I said we were going to deal with fast Fourier transforms and use bandwidths down to just a few hertz. At the same time, the Doppler shift of the moon is doing something like this over a day, 20 kilohertz plus to 20 kilohertz minus. It's varying about 1 hertz per second at its worst case, and you've got to cope with that. Now, the WSJT program allows, we did have a bit of a problem in the accuracy of the Doppler correction until Joe used his contacts in NASA to get a better model of what the moon's doing. But we can now send signals to the moon and back with GPS locking of frequencies and get within about 5 hertz at 10 gigahertz accuracy. After we compensate for Doppler, which is varying between 20 hertz plus and minus 20 hertz, and we do that using the cat control on our most modern transceivers. So in effect, by the time you take you correct for the Doppler shift, you get rid of that problem. But that's one of the things that is, the Doppler's proportional to frequency, so by going up in frequency, it's costing you a lot of trouble in terms of correcting for Doppler. Now, this is what the moon looks like if you were at the centre of the Earth over a sort of a monthly lunar cycle. Now, you can see the moon's wobbling around, and that's because the moon's pear-shaped and the bulbous part of the pear is pointing towards the Earth. But because it's going around in an ellipse, the heavy bit at the bottom gets more momentum at one part of the ellipse than the other, and so it wobbles around. Now, you're getting different Doppler shift from one side of the moon to the other, and it's all varying all the time. The Doppler shift for the moon is actually not the worst problem. The worst problem is we're actually moving on the Earth, and when we go from one side of the Earth to the other side, the Doppler can, relative to one side of the moon, is varying, and the end result is you can get up to 200 hertz of spreading of the signal from one side of the moon to the other. Now, here we're going to use very narrow bandwidths, and all of a sudden all our energy spread over from one side of the moon to the other. Fortunately, there are times when the movement of the moon is cancelled out by our movement on the Earth, and we get a null, and that allows us to choose the right time for QRP. Now, this is an example of what a signal off the moon, this is the JT4 mode, which has 4 tones, and on the bottom part of the slide you can quite easily see the 4 tones, and that's when the spreading has almost cancelled out, and there's only 2 hertz of spreading of the signal, and it's very clear. At the top, I'm not sure that you can see the 4 tones, but with a bit of imagination you can. And you can imagine that it's much more difficult to decode the signal at the top when it's spread. So again, if you want to do QRP, you've got to choose a time when the moon's wobble is cancelled out by our movement on the Earth. So this brings a whole lot of astronomy into ham radio as well as computing. And now some clever people have worked out what the spreading will be over a month and written a little program, open source. And this shows you what the spreading is. You see, in this case, it's between me and the guy in England. Sometimes in the month, it's over 100 hertz spreading. Other times, it comes right down to just a couple of hertz. And that's when you want to do QRP. Now, that means you only do QRP once a month, and you've got to get it all right down to that at that time. It's complicated by the fact that the window I have to Europe, the moon's nearly gone down before it comes up in Europe. So I've got to pick a time when we both can see the moon and the libration, the relative libration after the Earth's movement and the moon's movement almost cancels out. Now, you can even optimise the degree of cancellation by moving around, going portable. And so this is the sort of difference that it makes. Here's a day when it was very low, the libration spreading. If you're in the middle of New South Wales, you get it right down to zero. But if you move, say, to Sydney or Broken Hill or Melbourne, there's nearly 6 hertz spreading. So again, your options for doing QRP can be improved by going portable and selecting the right place. Right, now, with these are some of the variables that are involved in setting up what we call SCEDs. Between 5 hertz spreading and 160 hertz spreading, it costs you about 6 dB. The lunar degradation from the best to the worst, 2.3 dB. The moon noise on the large dish costs 2 dB. It means from the best to the worst case, there's about 10 dB difference by choosing the right time to do this stuff. And it means, for instance, under really good conditions, you can get down to 2 watts. And when the conditions are poor, you need 20 watts. And here's some other examples. Between my 77 centimetre dish and a 3 metre dish, I've used that as a reference, 2 watts to 20 watts. If you go up to a 77 centimetre dish to a 1.2, which is another dish I have, you need 15 watts, and under worse conditions, you need too much. Go from a 1.2 to a 3 metre dish, you can get down to 1 watt. And these are the sort of dishes that, you know, you can run from home on a balcony. And now, by going portable, I travel around Australia, and this is one station in Europe who's very keen. He's got a lovely website where he records all the grid squares that he's worked. And so you can see, I can see on his website where he's worked me. In fact, 2 of those grid squares were worked by stations other than me, but essentially all of those are a result of me travelling around and working portable EME. You'll notice some black dots there. Now what I've done there is I've deliberately set up so I was as close as possible to the corner of a 4-grid square and moved between the 4 on one moon pass. So that means setting the station up, moving and so forth. And I mean, you can't actually be right on the middle of a 4-grid square because usually that's in the middle of a paddock. You know, you might only have 2 hours, but by the time you set up your station and you move and you align everything on the moon, it is possible to get 4 grid squares in a single moon pass. So my conclusions are that you can work 5-watt QRP between, say, an 80 centimetre dish and a 3 metre dish when the libration spreading is low. There's about 10 dB variation from worst to best to worst conditions. The new mode QRA offers the potential of another 1 to 2 dB improvement, and it still has averaging to be implemented, which might do even a little bit better by averaging over different periods. I think, okay, what have I done? Well, no, that's nothing to do with my stuff, but there is something, that's your background, but just trying to relate that to this conference, which is, first of all, the programs that allow all this to happen are all open source. They are available in Linux as well as Windows. I have to admit, despite Scott's best efforts, I'm still a Windows fan. In terms of some of the things that can be improved where open source might be interesting, one of the things we're working on is if it's a cloudy day, you can't see the moon, you can't track it manually, you've got to have some way of tracking it. With a small dish, you don't get enough moon noise to track it. So you've got to have a way of accurately setting a bearing. Now, normally I find a farmhouse and on Google Earth I work out exactly what bearing it is. And when I get there, a farmhouse looking down on Google Earth is nothing like a farmhouse when you look on the side of it and you don't know where it is. But with a bit of effort, if you've got enough time, you go and find the farmhouse and you get an accurate azimuth bearing. Elevation's easy enough, you use an inclinometer. But one improvement which a couple of us, well, I can't say I'm really working on, I've planted the seed for somebody else to work on, is there's a U-Blox GPS system which I think's been developed for things like drones, which gives very high accuracy differential bearings. And it has a little 433 meg transmitter between the 2 units. And you could go out, say, 100 metres with one of these and with a post, and then sight your rifle scope at it and get a very accurate bearing. And so that's an area where it's important. The other area that's a real problem for me is this program depends on accurate timing. Now, someone earlier here talked about nanosecond accuracy of GPS timing. I'm not looking for nanoseconds, but I am looking for reliability. So I know when I'm out in the bush that it's exactly right to within, I did have a goal of being within a millisecond. I've changed my goal to being happy with 100 milliseconds. I have tried for the last 2 years to produce a GPS time that's simple and reliable, and everyone tells me there's stacks of things that do this, and I have bought 3 or 4 commercial systems. Yes, and I've got 5 minutes to go, thank you. I have not got a reliable system. It's amazing how often they will jump by a whole second. that they just decide that they can be milliseconds right in terms of the 1 pulse per second, but they don't know which 1 pulse per second, which 1 second the damn thing is. That's been, I'm spending far too much time on solving that. I did at one stage think that if I could get accuracies down to better than the millisecond, I wouldn't have to send a sync pulse for timing. And the WHJT modes, like JT65, it spends half its energy sending sync. So if you can get rid of sync and have accurate timing, you've immediately picked up 3 dB. I'm not even worried about, I mean, that's a long-term plan to find the 3 dB, but the short-term plan is just reliable. I should say I do have a very reliable system that works on XP, but everyone tells me XP's probably had its day, and I can see that's going to be a problem. Okay, I've probably only got about 3 minutes, but I'm very happy to answer questions.
Cool. Have we got any questions here? Maybe one question, Paul? Right. Cool. Well, we've got to sort of finish it up soon anyway, because we've got the Linux Australia AGM shortly after the close here. But I'd like to thank Rex for coming along and telling us about how to get some information up to the moon and back. And